Welcome on this video about relation, mapping and functions. Today we have many goals, mostly three categories. First, relations, second, functions, and third, polynomials. For the first topic, relations, there are really two things which are important. Understanding what a relation is and what an equivalent class is. What are relations? We are going to see many properties, but don't worry, we are going to order them and it's going to be a lot easier to remember them. Then we will see how to visualize them, and this is going to make the concept of relation really easy to understand. Then we are going to see how we can use these properties to prove that something is a special relation, and by special you're going to understand what I mean in a few seconds. Functions. We are going to see three properties: injective, surjective and bijective. Then we are going to see what is the inverse of the function and how to build it. I am also going to make you aware of a trap, polynomials. It's going to be the fastest chapter because we are going to see how to make fast calculations and how to factorize them and give a special polynomial with roots. We are not going to see polynomial division because it's a slow method and I already spoke about it in the third video. Let's start with the relation. I think it's best to understand relations with a guided exercise. So we consider the relation R on the set M. Here is the set M. 1, 2, 3, 4, 5. And here is a relation. It's a set of tuples and it's part of M cross M, the Cartesian product. If you are not sure what the Cartesian product is, you can look at my other video about sets. To do the first question, which is it an equivalent relation? You just write 1, 2, 3, 4, 5 in a cycle, and you link the numbers together according to this. So for example, you can link, and 1 is just one arrow, and 1 and 2 would be the arrow in the other direction. So you do that for everything. And after that, for the first question, you look if these properties are true. Flexibility, symmetry, and transitivity. Flexibility is when each number is linked with oneself. So when you see an arrow like that on a number. Then, symmetry is if you see such an arrow. It means that when A is linked to B, then B is linked to A. Then transitivity, if A is linked to B and B is linked to C, then C is linked to A. And for the second question, you look which number are linked together. Here you go, try it out. Okay, now I'm gonna correct it. So here is how it looks like. And you see that the three properties are true because each number is linked to himself. And if A is linked to B, B is linked to A, this is true because 5 is linked to 1 and 1 is linked to 5. 2 is linked to 5 and 5 is linked to 2, etc. And transitivity is also true. For example, here you see it. 2 is linked to 5, 5 is linked to 1, 1 is linked to 2. But it's also true here even though we have only two elements, because here, for example, if you start from 3, 3 is linked to 4, 4 is linked to 3, then 3 is linked to 4. So R here is an equivalent relation. Now, for building the equivalent classes, we want to see which numbers are linked together. So here you see these numbers are linked together and these numbers are linked together. So we have two equivalent classes. Let's write them down. So how do we write them? We are just gonna call them the name of one represented. I can choose 1, 2 or 3, for example, for these ones. I'm gonna choose 1, for example. And this equivalent class contains 1, 2 and 5. What about the second equivalent class? I'm gonna choose the number, let's say 3, but I could also choose 4 as the representant. So this is the name of the class. It contains 3 and 4. To be more precise, in math, we are not gonna say is linked to. We are going to say is in relation with. So what do we have to remember? We already saw equivalent classes. They are reflexive, symmetric, and transitive. Reflexivity, it's when an element is in relation with oneself. This element is part of this set. So two ways of writing it down. I prefer the first way, so I'm gonna use it. For symmetry, when A is in relation to B, then B is in relation to A. For transitivity, A in relation to B and B in relation to C, then A in relation to C. For remembering, I would just say, remember RST, because reflexivity, symmetry, and transitivity. If you replace symmetry with antisymmetry, so you have reflexivity, antisymmetry, and transitivity, mnemonic rat, you have a partial order relation. Think about this relation, because it satisfies the antisymmetry for all A, B of M. If A is in relation to B and B is in relation to A, then A equals B. And this is true for inferior equal, because if A is inferior equal to B and B inferior equal to A, then A equals B. To make it even more, so to G, the first is for transitivity, you know this one. A is in relation to B and B in relation to C, then C is in relation to A. And total means that for all AB of a set, A is in relation to B or B is in relation to A. For example, if you have such a thing, then there is a problem. It's not total because this thing is left alone. If you want to make it total, you have to add the reflexivity. You want the antisymmetry, which means that there are no arrows like that. You want the transitivity, and then you want it to be total. So it will look like that. Be careful, because antisymmetry is not the same thing as symmetry. Not symmetry would mean that for all A, B, R is in relation to B implies not this thing. So B is not in relation to A. Which means that, for example, if you have A in relation to A, then A is not in relation to A. The relation does not allow reflexivity. But in antisymmetry, it's possible. Let's choose A and A. So A is in relation to A and A is in relation to A, right? Then A is equal to A. Let's practice relations. If you have an integer A that is in relation with B, an integer, then A minus B is divisible by 5. Now I want you to do two things. One, I want you to show that R is an equivalent relation. And B, I want you to tell me what are the equivalent classes for these relations. Pause the video. That's correct. So the reflexivity, A is in relation to A, means that A minus A, which is 0, is divisible by 5. And since 0, it is divisible by everything except 0, of course, then it's true, because we have A in relation to A. Now the symmetry. Let's take two integers, and we start with A is in relation to B, and we want to end with B is in relation to A. What does it mean? B minus A divisible by 5. And we're gonna get it. How? A is in relation to B means that A minus B is divisible by 5. By definition of divisible by, it means that there is an integer k, so that A minus is 5k plus 0. So if you multiply by minus 1 on each side, you get B minus A is equal to 5 times minus 1k. But I can call it k prime, for example. And this is an integer. If you want to be fancy, it's because of the closure of the commutative group integer plus. But that's we're gonna see in tomorrow's video. But you don't have actually to tell it. It's like obvious that minus 1k with k in integer is an integer. We have proven the symmetry. Now the transitivity. Let A, B, C be integers. In German you can say seien A, B, C ganze Zahlen. Then we want from this to get this. This is the definition of transitivity. How do we get there? We do the divisible definition for A minus B and B minus C, because A is in relation to B, so A minus B is divisible by 5, so there is such a K1 verifying that. There is the same thing for B minus C, so there is a K2 verifying that. Just add here, add the right part together, the left part together, then the B cancel, and you have then A minus C, 5 times something that is an integer. Therefore, we have A minus C divisible by 5, so A is in relation to C. And we have proven, therefore, RST, which means equivalent relation. For the equivalent classes, when it's divisible by something, it's actually really easy, because there are always n, here n equal 5 equivalent classes. So here, the equivalent classes are, I would call them 0, 1, 2, 3, and 4. These are the rest by the division by 5. So for example, 0, 5, 10, etc. And this is all for the relation part of this video. One part done. Yoo-hoo!